Okay, now we're going to take a look at how we can use derivatives to solve bigger problems. The first thing we're going to look at here is how to find extreme values of a function, so to find the largest and the smallest y values. Here's some advice from past students. Halloween's coming up, make sure you're here. Okay, so we have absolute, which are also called global extreme values. These are the biggest and the smallest values that the function will take on over its entire domain. So the absolute or global max is the absolute largest y value. The absolute or global minimum is the absolute smallest y value. And we often refer to these as absolute extrema. Okay, let's just take a look at what this can look like on a graph. So here's y equals x squared from negative infinity to infinity. Absolute minimum right there at 0, 0. There are no absolute maximum values because this function continues upward without bound. If we restrict the domain from 0 to 2, including both endpoints, we have an absolute minimum and an absolute maximum. If we make the left endpoint open, there's no longer a minimum value. Even though it approaches a value of 0, it never gets there. And there's an absolute maximum. Both endpoints open, there are no extreme values, no minimum, no maximum. And so here's our extreme value theorem. If a function is continuous over a closed interval, then the function has a maximum and a minimum value over that interval. And just notice the two conditions we need here. The function must be continuous and the interval must be closed, meaning the endpoints must be included. Here's some examples of what this can look like. You could have max and min at interior points, at exterior points, or maybe a combination of the two. Okay, we can also have what we call local or relative extreme values. So these aren't necessarily the largest number overall, but within some open interval. So in relation to the points nearby, it's the largest or the smallest value. We can see what this looks like right here. So we have an absolute minimum, because it's the smallest y value. Absolute extrema are also local extrema. This would be a local maximum because, although it's not the biggest y value overall, in the open interval around this point, it is the biggest. Local minimum, absolute maximum, which is also a local maximum, and a local minimum. We want to think about what it takes for there to be a local max or a local min at an interior point. You can see with these first two, the slope is 0, so f prime equals 0. At this top point, f prime does not exist. So if a function has a local max or a local min at an interior point, then the derivative has to be 0 or not exist. There's no other way for us to have a max or a min. Whenever the derivative is 0 or does not exist, we call this a critical point. And just notice that this theorem does not work backwards. So max and min points in the interior of a function always occur at critical points. But just because you have a critical point doesn't mean there's necessarily a maximum or a minimum. Here's an example where we have a critical point, but it's not an extreme value. Here's another example. We have a critical point because the derivative is undefined, but it also is not an extreme value. So just because you have a critical point doesn't necessarily mean that you're going to have a max or a min. Okay, let's find any extreme values for this function. So we should find the critical points because those will tell us where the extreme values could possibly occur. So we take the derivative, let's factor, and then we can set it equal to 0, and from the factored form we can see that we have critical points at -2 and +1. If we use a number line, we can examine the derivative. If we choose a number to the left of -2 and plug it into the derivative, we get positive, which tells us the function is increasing until we get to x is -2. Plug in a number between -2 and 1, we get negative, so the function is decreasing. Plug in a number greater than 1, we get a positive, and the function is increasing again. So our function goes up, then down, then up, so we can tell that x equals -2 gives us a maximum value, x equals 1 gives us a minimum value. And we can find out the actual values of these. So a relative max, f of -2 is 24. A relative minimum, f of 1 is -3. Okay, we could deal with something that's on a closed interval. So here we have our function from -1 to √8. So we take our derivative, set it equal to 0, and we can find that this is undefined when x equals 0. So we have a critical point at 0, 0. Now, we could use a number line to investigate increasing and decreasing, but since we're on a closed interval, we have to check those endpoints anyway to find out what their values are, so we might as well just go straight to that. So let's check the endpoints. The y value when x is -1 would be 1. When x is √8, we would get 2. And so we don't need to use a number line at all, because we know our one critical point, and we can see that the values to the left and the right are larger, making our critical point a minimum. Absolute minimum of 0, 0, absolute max of √8, 2, and a relative minimum of -1, 1. Here's the graph of the function we were just looking at, so you can visualize what those maxes and mins look like. Here we have a function over an open interval from -1 to infinity. So let's take the derivative, factor, and set it equal to 0. So we identify our critical points. We can plug those back into the original function. We should also check our one endpoint. Even though it's not included, it's a good idea to know what the value is, which is -3. And we might also use a number line to help ourselves out here. We can plug numbers in each interval back into the derivative to find increasing and decreasing. So we know where we have our max and where we have our minimum. And then we can summarize our findings here. So in general, if we want to find maximum and minimum values, we take the derivative to find the critical points. And we can then investigate the critical points. So we can either look at the actual function values, or we can use a number line and investigate if the function is increasing or decreasing.